Hello everyone, this is a video going through all of the challenge questions in Edexcel's Pure Year 2 textbook, Chapter 5. Okay, so first of all, from exercise 5a, we're asked to describe all of the angles theta in radians that satisfy A, cos theta equals 1, B, sin theta equals minus 1, and C, tan theta is undefined. So first, let's draw out each of these graphs. So we have sine of theta looking like this. So starting at the origin, going down and up, and it repeats every 2 pi radians or 360 degrees. So that's sine theta. Then for cos theta, we have a similar pattern, but instead of starting at the origin, we start at 0, 1. Then we go down and back up. Then the same on the other side, as it repeats every 2 pi radians again. So that's cos theta. Then tan theta, you should know, has asymptotes at every pi over 2 radians or 90 degrees. And it looks sort of like this, where the graph tends towards the asymptotes. So that's tan theta. So if you think about where cos theta equals 1, then that will be at all of these points, the maximum points, which you know from the graph are at 0 degrees, 360 degrees, and minus 360 degrees, or in radians, 0 radians, 2 pi radians, and minus 2 pi radians here. And so we can write all of the angles as multiples of 2 pi. So theta equals 2n pi, where n is an integer. That's what this said thing means. So any multiple of pi, essentially. So that's one concise way we can write the solutions. And for sine of theta, we'll have this being equal to minus 1 for part B. So that's all the minimum points this time. And they occur here at 3 pi over 2, here at minus pi over 2. And we can see that this will repeat every 2 pi again because of the period of sine theta. So here we can write theta being equal to 3 pi over 2 plus some multiple of 2 pi again. So where n equals an integer. Okay, and finally for tan theta, where this is undefined, so we have an asymptote here at pi over 2. Then there are more asymptotes every pi radians after that. So here at 3 pi over 2. Here at minus pi over 2, and here at minus 3 pi over 2. So again, we can write our solutions in a similar way. So theta equals pi over 2 plus some multiple of pi, where n is once again an integer. Okay, for exercise 5D, we're asked to find an expression for the area of a sector of a circle with radius r and arc length l. So if we imagine what that sector looks like, sorry, it's going to be wonky there, but we have this angle theta here, and we have the arc length l and the radius r. And we're asked to find an expression for the area of the sector, which we know in radians is a half r squared theta. And we also know the arc length in radians is r theta. So to find the area in terms of just r and l, then we can say, well, the area is a half r squared theta, so that's a half times r theta, and then we can just replace r theta here with l, which also equals r theta, so we get finally that the area is equal to a half r times l. Okay, the next question is from exercise 5F. Question 1. The diagram shows a right angled triangle ABC, and the angle BAC equals theta. An arc CD of the circle of centre A and radius AC has been drawn on the diagram in blue. In part A, asks us to write an expression for the arc length CD in terms of AC and theta. Well, AC here is the radius, and we know that the arc length is equal to theta times r, or r theta, in radians. So the radius here is AC, and the angle is just theta. So we've got the arc length in terms of AC and theta as required. Now part B, we're told that given that theta is small, AC is equal to AD is approximately equal to AB, and CD is approximately equal to BC. Deduce that sine theta is approximately equal to theta, and tan theta is approximately equal to theta also. So what this is saying here is that given that theta is small, so as theta gets smaller and smaller and smaller, you can imagine the right angle triangle sort of collapsing downwards, then AC equals AD, so the radii are approximately equal to AB, so they're approximately equal to the hypotenuse of the right angle triangle, and CD is approximately equal to BC. So this arc here, as theta gets smaller and smaller and smaller, gets closer and closer and closer to just being the straight edge BC. And we can use these facts almost like differentiation from first principles. So as theta gets smaller and smaller and smaller, we get a better and better approximation. So sine of theta, using right angle trig, we know that's the opposite. So BC over the adjacent, the hypotenuse, which is AB. And we know this is approximately equal to, well, BC is the straight edge that we know is approximately going to be equal to the arc length, CD, as theta gets smaller and smaller and smaller. And we know AB as the hypotenuse is approximately going to be equal to the radius as theta gets smaller. So that's approximately equal to AD or AC. But if we use AC here, when we plug in the value for CD as the arc length up here, then the ACs will cancel. And we're just left with theta. So sine theta is approximately equal to theta as required. And we can do a similar sort of thing for tan theta. So tan theta, using right angle trig again, is the opposite BC over the adjacent, which is AC. And once again, BC is approximately equal to CD, and we get the same result here. So CD is AC times theta over AC, so we're left with tan theta once again being approximately equal to theta, as required. Now for exercise 5F, question 2. Part A says using the binomial expansion and ignoring terms in x to the power 4 and higher powers of x, provide an approximation for the square root of 1 minus x squared, where the modulus of x is less than 1. So, using the binomial expansion, here we have 1 minus x squared to the power of a half. Now we know this is equal to 1 plus the power times the x, which is actually here minus x squared. Then we're going to add on to that the power times the power minus 1, which is minus a half, over 2 factorial, or just 2, times the x, which is minus x squared again, all squared. And remember here we're ignoring terms in x to the power 4 and higher, and this will be a term in x to the power 4, so we can actually ignore that. Okay, and these first two terms, we're going to have 1, and then we're going to have minus a half x squared. And those are the only terms that we're worried about. So we can then use this in part B to show that for small theta, cos theta is approximately equal to 1 minus theta squared over 2. And it says here you may assume that sine theta is approximately equal to theta. So we can see the square root of 1 minus x squared by telling us we can assume sine theta is approximately equal to theta. They're giving us the clue to use the identity that 1 minus sine squared theta is equal to cos squared theta. So actually, if we plug in x equals sine theta here, then we get the square root of 1 minus sine squared theta, which is the square root of cos squared theta, which is just cos theta, is approximately equal to 1 minus a half x, which is sine theta, squared. And because sine theta is approximately equal to theta, or sine squared theta is then going to be approximately equal to theta squared. And so we have cos theta is approximately equal to 1 minus theta squared over 2, as required. Okay, and finally, for mixed exercise 5, we're given these three equations here, and we're asked to use these small angle approximations to determine whether the following equations have any solutions close to theta equals 0, so essentially theta being a small angle. And we're told to state whether each root of the resulting quadratic equation is likely to correspond to a solution of the original equation, so basically if theta is small enough or not. Okay, so for part A, we have 9 sine theta, and sine theta is approximately equal to theta, times tan theta, which is again approximately equal to theta, plus 25 tan theta, so 25 theta is equal to 6. And this is the equation we can use to approximate the original trigonometric one. So here we have 9 theta squared plus 25 theta minus 6 being equal to 0. And here you can factorize into the two brackets 9 theta minus 2 and theta plus 3 being equal to 0. So we have theta being equal to 2/9 or theta being equal to minus 3. Now, which of these are valid? Well, theta equals 2/9 is pretty small, so that's a tick, but minus 3 is a bit too big, so this is probably not a solution to the original equation. Okay, for part B, again, 2 tan theta is approximately equal to theta, plus 3 equals 5 cos of 4 theta, and now here we have to be careful, this is 5, and the approximation for cos theta is 1 minus theta squared over 2, but here theta is actually 4 theta, all squared over 2. Make sure you include the brackets everywhere. And here we have 2 theta plus 3 then is equal to, well, 5 minus 4 theta squared is 16 theta squared times 5 is 80 theta squared over 2, so 40 theta squared. And again, we can rearrange and solve. So 40 theta squared plus 2 theta minus 2 is equal to 0. So 20 theta squared plus theta minus 1 equals 0. And here again, we can factorize into two brackets, which are 4 theta plus 1 and 5 theta minus 1. So we have theta being equal to minus a quarter or theta being equal to 1/5. And because they're both relatively small, we can tick them both. They are both likely to correspond to a solution of the original equation. And finally, part C, sine 4 theta, which is approximately equal to 4 theta, is equal to 37 minus 2. Here, remember your brackets again. Cos 2 theta, 1 minus 2 theta, all squared over 2. So 4 theta is equal to 37 minus 2 plus 2 theta squared is 4 theta squared over 2 is 2 theta squared. Then multiplying by minus 2 gives us plus 2 theta squared. Then rearranging here, 2 theta squared minus 4 theta plus 35 equals 0. And actually here, if we work out the discriminant, b squared minus 4ac, we have 16 minus 4 times 2 times 35, which is minus 264. This is less than 0, so actually there are no solutions. And that is the end of the challenge question walkthrough for this chapter. I hope you enjoyed, and I'll see you in chapter 6.